In this problem from JEST 2022, we have high energy neutrons scattered from a metal lattice. The spacing between nuclei is around 0.4 nanometer. We have to find the order of kinetic energy of neutrons to see the quantum diffraction effects. We can use the condition of diffraction here. Condition of diffraction is lambda is approximately equal to d. Lambda is the wavelength of light and d is the slit width. This is in the case of diffraction of light. But here we are not discussing diffraction of light. Here we are discussing diffraction of particle. We know that matter can have dual nature. It can have particle nature and wave nature. And the wavelength of particle, it is given by the equation, de Broglie equation, lambda is equal to h by p. So the lambda here is de Broglie wavelength and d here is not slit width. This is not classical diffraction. This is quantum diffraction, and in quantum diffraction d is the spacing between nuclei. Therefore we have lambda is approximately equal to 0.4 nanometer. Now we can find out P. P is equal to h by lambda. This is equal to 6.62 times 10 raised to minus 34 joules second divided by lambda is 0.4 nanometer is 10 raised to minus 9 meter. Therefore this is equal to 1.655 times 10 raised to minus 24 kilogram meter per second. Now we know the momentum. We can find the kinetic energy. Kinetic energy in non-relativistic case is kinetic energy is equal to p square by 2m. This is non-relativistic case. In the relativistic case, we have kinetic energy. Kinetic energy is equal to total energy minus m naught c square. Total energy minus rest mass energy. Total energy is given by root of p square c square plus m naught square. M naught square is the rest mass, c raised to 4. This is how we find the kinetic energy in relativistic case. Now in this problem, are we dealing with relativistic case or non-relativistic case? To decide that, we can compare momentum compare P to m naught c. If you are given velocity, then you should compare it with V with c. If you are given energy, then compare E with m naught c square. To decide if the case is non-relativistic or relativistic, if you are given momentum, you should compare it with m naught c. If you are given velocity, you should compare it with c. C is speed of light. If you are given energy, you have to compare it with m naught c square. And if V is very less than C, this is non-relativistic. If V is comparable to C, then it is relativistic. If E is very less than m naught c square, then it is the case of non-relativistic. If P is very less than m naught c, then it is a case of non-relativistic. Let's see if P is very less than m naught c or not. P we found was equal to 1.655 times 10 raised to minus 24 kilogram meter per second. M naught c is equal to mass of neutron is 1.67 into 10 raised to minus 27 kilogram, and c is equal to 3 times 10 raised to 8 meter per second. This is equal to 5.01 times 10 raised to minus 19 kilogram meter per second. You can see that 1.655 into 10 raised to minus 24 kilogram meter per second, it is very much less than 5.01 into 10 raised to minus 19 kilogram meter per second. Therefore, this is a non-relativistic case. And in non-relativistic case, we can use E is equal to kinetic energy is equal to P square by 2m. P is already found, which is 1.655 into 10 raised to minus 24 kilogram meter per second whole square divided by 2 times mass is mass of neutron, which is 1.67 into 10 raised to minus 27 kilogram. This is coming out to be 8.2 times 10 raised to minus 22 joule. Now we have to find the energy, the kinetic energy in terms of EV. 1 EV is equal to 1.6 times 10 raised to minus 19 joule. Therefore, we have kinetic energy is equal to 8.2 times 10 raised to minus 22 joule times 1.6 into 10 raised to minus 19 joule. 1 EV in the numerator, joule cancels. In EV, kinetic energy is equal to 0.005 1 EV, which is equal to 5.1 MeV, 5.1 milli electron volt. Therefore, the order of kinetic energy is in MeV. Option A is the correct answer here.